I'd like to introduce Morris Historian. He's been with EMC for the last 10 years with the data analytics team. He's going to give us a presentation about the EMC product.
Okay, Assalamu alaikum everybody. Okay, so I'll be taking you through big data, basically the Deluge, Tofan in Arabic, and hopefully also I'll give you something about the perspective from an industry perspective, or what are the different variables that we need to consider when we look at things like big data analytics, and the infrastructure beneath that. The doctor and my colleague from HP has already very eloquently explained the software layer that does the inside analytics. So I'll just take this opportunity to. Sorry. Okay. So I'll take this opportunity to give a very sort of quick and a high-level details on what we have underneath it from technologies, mainly from the software side. So very quickly, we already, I think the gentleman, my colleague from HP, already discussed the characteristics of the attributes of today big data. That something that is extremely fast velocity. That in the industry they call the 3Vs. Some people might add another V like vulnerability, etc. But primarily, I make it simple. Big data is all about data that is very fast coming in, data that is today what we call streaming data. The volume of the data has jumped from petabyte, some people go exabyte, zettabyte, but a lot of bytes coming after that. And then finally the variety, structured, unstructured, semi-structured. Quickly, semi-structured is typically from a computer science people, typically XML type of data, or a data that has been extracted from our classical RDBMS and put into some sort of a document. That's the sort of semi-structured data. A different way of looking at it, sometimes the industry looking at it, especially the business, the CXO type of people in the companies or the enterprise, things like how we integrate, we need to integrate across the broad range of data streams, video, audio, text, the whole lot, including classical enterprise data. Things like that, we need to interact with it in real time, near real time, and probably things like if I want to do some insights to it, like if I want to do sentiment analysis to a huge amount of a repository of data. So some people will look at it in this 3I perspective. And finally, people like from the industry leaders, both CXOs, foresters, gardeners of the world, they look at it from a cost, revenue possibilities, opportunity risks. These are the different perspectives. They look at big data, and we still haven't looked at analytics yet. That will be coming soon. And then something's coming. I mean, this is again from Google Trend, and if you can see the crazy demand for things like a data scientist today. That's a new role that has been created as part of this deluge of big data, this new wave of big data, which is part of this what IDC calls it the third generation, the third platform of IT innovation. So. And then there is a new, even on the CXO level, there is a new role, new position being sought and looked at, the big data, chief big data officer coming into the field. Again, some of the quick concepts. I'm not sure if you guys look at there's a magazine, Economist magazine. Today, such magazines are coming up with really nice words. So we're looking at things like infonomics. Yeah, so it's no longer economics. So what are we? And one of the aspects of one of the things it looks at is how can we take a data and make it an asset rather than just being a liability and just pay for it, for backing it up, replicating it perhaps, etc. And then when we look at big data, and that's when in this slide I introduce analytics. Sorry. Basically, when we look at big data analytics, that means when we have this big data repository, and then we add analytics to it from the gentleman, my colleague from HP that has mentioned it. What we get is the value of that. That's what adds the value, and that's what we get our assets. And then when we break down, so I have this repository, which is typically a computer science type of repository. It's an IT repository where I put all data. I store them in one way, in one form or another, and I put all types of data. It's a raw repository, structured, unstructured, and semi-structured. And then there is the analytics part. Analytics part, basically the word analytics, and this is a Wikipedia sort of explanation, basically the systematic, either mathematical, social, medical, chemical, etc., computational analysis. So if we break this, this is typically coming from a data scientist, which comes into these type of verticals: health sciences, security, CCTV, etc., environmental, aeronautics, social, chemical. So for us to be able to leverage or to have some really algorithm to understand what to put in this analytics, we need to understand some data scientist knowledgeable in these verticals have to be aware and coming up with this. And liaise very much with the mathematics of this world, and the statisticians of this world, to be able to come up with this algorithm in order to join this big data fabric, and then gives us the value. And then if you see the last part is where our computer science portion comes up, and that's what I call AKA information technology. So this slide basically showing the perspective when we talk about big data analytics. There's a lot that has to be put in perspective first. It's not that one person will do the analytics, regardless what type of analytics we're looking at. The data scientist plays the skills and the expertise of data scientists, and its focus area plays a big role here. The other quick one is, if we look at analytics today, is data mining, etc. It's just an aspect of the analytics. And then today we see there is a roadmap, there is a progression that one can consider to take as a journey, ending up with what we call prescriptive analytics, something that analytics not only tells me things, but it goes and executes it for me. But today, what we look at, if you look at the classical enterprise, business intelligence, EDW, enterprise data warehouse, we're somewhere in this between having in hindsight, looking at our, in the car from our mirror looking backwards, and somewhere quite coming close looking forward. The industry is trying today, 2014 probably will be very much picking up into this, and we'll see how we'll see where we stand with that. But that's another perspective to consider. Besides the focus vertical, how far where we're going to start in analytics, how far we're going to take it, and it can go pretty far today. Again, how big is the data? There's a big numbers. That's easier. For example, I've seen one of the reports saying that 2012 we have something 2 million petabytes allowed. Projection 2020, 35 million petabytes, fine. But then I just tried to look at what sort of rate we have per year. The number is khayali, it's quite a big number. So I just, but the important part, and I think I go with my colleague from HP, is 80% of that is completely unstructured data. Movies, videos, text, including our classical structured data as well. And then I just put, we in EMC, we like to every now and then look at this Gartner hype cycle. Basically, it shows this new wave of technologies. Where do they stand for this Gartner's notions of the cycle? Basically, everything starts with very, extreme anxiousness on the innovation and starts climbing out. So I started looking at big data, which is the thing in red, 2012, 11, 12, and 13, and you say, we're pretty much, we are interested. But then quickly, 12, 13, big data jumped. Now, the interesting part of it is the Internet of Things. That is basically the machine-to-machine type of a communication that uses internet, or the information that gets exchanged between non-human part of this information contribution was really before big data. The market was really more anxious about that. Coming 2012, big data put it way back behind, and now we are pretty much at the peak of this global anxiousness and expectation from this technology, from this wave of technology as well. And if you look at predictive analytics, it's still slightly trailing, slightly behind the big data. So, just a side note, cloud computing have reached here. Just on the side note, it has really went into that acceptance of the market and it starts rolling itself into it. And most of the IT departments of this world is no longer strategizing and planning, and they're just more into the execution and deployment and the lessons learned from there. So, sorry, I forgot this one. Sorry. Let's look at the underlying landscape, technical landscape. The underlying landscape, I think, what are the components that we need to consider? So we looked at the perspective from the data scientist knowledge area. We looked at where the analytics, how far, how much of the analytics, how extensive of the analytics we want to do. Let's look at what sort of the whole ecosystem of this big data analytics underneath has, and there could be decisions and opportunities and challenges that has to be looked at underneath that. So we have the classical Internet of Things, your Twitter, Facebook, YouTube, whatever, coming into this, into your sort of a big data ambition inside the enterprise or inside an organization as big as a government, for example. And then you have the different structures starting from classical internal IT, which we know, the emails, the CRMs, the ERPs, and the documents that we have, the internal CIO, CTO domain that they want to protect and keep very comfortable. And then there is this area that's really becoming a monster, basically having a virtualized complete infrastructure underneath from the compute, storage, etc. And then here in the industry, there is the well-known wave of defined of things are coming in. Everything has to be software defined. Automation, orchestration has to be baked into the technology, not plugged on top of that. Then we have the Hadoop, and we'll talk about it. Or let's say, what is our data fabric to store of this type, to dump all this structured and unstructured data into it. And in the industry, it talks about things like data lakes that you put things on. And then you have the engines, the software that's going to process in the best way this massive amounts of data that's coming very fast, very high volumes, and a number of varieties of imaginable and unimaginable. And then, so these are the three different technologies, things like real-time structured databases, databases names that we were, a couple of years ago, were not really heard of. MongoDB, Cassandra, HBase, yeah, Dynamo. These are different DBs that have come up based mostly and primarily, I think, from the IT industry for a, strangely enough, it did not really originate from sort of a university or the US Department, DOD, Department of Defense. And there will be a history brief about that. And then there is the classical analytics that I would like to do in near real time. And near real time, I understand, is relative. And then finally, the whole thing that started, if I have a Hadoop substrate, how would I do my sentiment analysis of, let's say, feeds that I'm getting across the different, or the streams that I'm getting across the different channels? And this is where it's more of this classical batch processing. On top of that, you'll see I need a visualization layer, which I need to present my findings in one way or another. And then I just added an option here. Today, there is more and more in the industry. We push things like analytics as a service. That means an organization can present analytics services to the market. And then the market, the consumer market, the retail market, the financial market can come in and request on a timely basis insight on some decisions that they need to do, either some sort of analysis on a certain aspect of it, and present the finding. So that's becoming something that the market is, every vendor, for example, like EMC, is really showing an acceptance, profound acceptance of. And particularly we see the anxiousness coming from the telecom industry. Um, I will jump into this very quickly. So, apologies. Here, each aspect of this, each block that represents this diagram can take the subject into hours of discussion. But I will be focusing just on this part, the Hadoop, what started it, to give a flavor of what challenges or opportunities, especially from an educational establishment, that it can have from a research and development, because all of these are basically research development results that has come up from the industry. There has been from the universities, but they're all contributions. And we will see that most of the things that here are currently in the Apache open source foundation, yeah, which they encourage research and development. So quickly on the slide, Hadoop. So I've taken just the Hadoop, the batch side from that slide, and I'm just going to go through the slides, the slides with it. And basically, it all started in Google 2003. They wanted to solve a very simple problem. How can I index the whole World Wide contents of the World Wide Web within minutes? Everything in it. So that was the challenge that the engineers they had, and they wanted to provide a solution for. And 2003 and 2004, that's where the Hadoop and the MapReduce technologies came up. Purely software, commodity clusters, and that's where the whole wave started. And it got picked up with this guy, Douglas Cuttings, and then he moved it in. He was an Yahoo employee, but he moved it into Apache, and that's where the whole thing, and it got open to the big open source community. And that's where the richness of this thing started coming up in every way possible. It's interesting to read what is this. It's a nice articulation of Apache Hadoop, but I will leave it because of the time constraint. I'm sorry there is a lot of text in here. So Hadoop consists of two main things, with being simplest. A file system in the simplest computer science, and the MapReduce computation framework or computation part. So I'm looking at the file system now, the Hadoop file system, and a rundown of the high-level features of this file system. Basically, it's something that can store millions and billions of files, of gigabytes and terabytes of files. And imagine if you have a file of a gigabyte, and this is the typical size of a file you store in your PC. And you want to keep and you want to retrieve it, perhaps do a spell check and close it. Probably have to leave it to have a lunch and come back, and maybe it crashed or it's finished. So, with the Hadoop file system, that's what's being built ground up. The other thing is, let's look at when you have in Hadoop file system, they break things starting at a 64 megabyte. If you consider today on an average Oracle database block size, modestly we started sometime a couple of years ago, 8 gigabytes, now it's 16, maybe 32, 128, 256 kilobytes or kilobytes. In Hadoop, things are megabytes. And I will show you why that is an important point. The file system is designed to be distributed across numbers of nodes, thousands of nodes. And the chunks of the 64 megabyte or more will be put across the different node clusters. So some of the description are at a high level out there. If you can see, and all the nodes are made of a commodity hardware. On the next slide, the premise of Hadoop file system was based that this thing is made to fail. So if I have 10,000 nodes and I have my cluster across 10,000 nodes, and I have typically a couple of hundred of petabytes of storage on it, I expect on a daily basis tens of servers to fail, and I am okay, and I can issue a request for a change on a weekly basis. So I can go and let my engineers change 20, 30 servers, and without being alarmed about it. If you reflect this in today's enterprise, you cannot afford having that. So there's a complete big paradigm shift that has happened when we consider big data, data fabrics, especially, and when I say data fabrics, it's typically on a Hadoop file system. What does it look like, the Hadoop file system, how things communicate? So we have nodes, two types of nodes at high level, a named nodes, and I have a data nodes, thousands of the data nodes, and typically named nodes in a version 2.0, these have become more highly available because everybody started complaining that this is a single point of failure, etc., etc. So what happens is, when I have my file is already distributed across the clusters of the nodes, and if I want to do a query for a certain word in a file, the query is sent across all the nodes that has that pieces of the file, and all the nodes responds back. So it shows that if I want to increase the performance of this, all I have to do is add nodes, and it scales out. And this is a new paradigm in. It's not new. It is a new paradigm in scalability, and that is Hadoop file system scales out. Every compute node we add, it contributes to the processing power. So at the end, if I want to retrieve or query any chunk of my file, of any data, it's all over. I have many nodes that can respond to it. And if that's going slow, I add more nodes. I spread more of my data across the different data nodes in a Hadoop file system. The other aspect of Hadoop file system is the MapReduce. So in a MapReduce today, it's basically the other side of the Hadoop coin. So I have the file system, and the other side is the MapReduce function. MapReduce data processing function that leverages that file system. And we need to have something extremely efficient. So just to give you an idea, I think I jumped ahead of myself. Something simple. So how long does it take to open a 100 gigabyte file on a PC? What happens if I do a spell check for it? And I need to do that on millions of files. Okay, so that's where the challenge that MapReduce solves. Yeah, and then I wanted to put a quick table of comparing the classical RDBMS, which is important and critical, and today's MapReduce. You can see there is a lot of points here which I apologize if it's not clear. Things like no SQL. This is not no SQL. This is not only SQL. So MapReduce process has a structured query language, but it can also talk to unstructured data as well. And that's where the no SQL is not only SQL, and some people call not an ordinary SQL. So, but you can see there are things that the MapReduce might not be applicable in the certain environment or objective that we're looking for. For example, if I go for latency, today's the MapReduce comparatively has a higher latency than, for example, RDBMS. That's the objective of this table to emphasize and highlight that today they complement each other. Whatever you were able to do, to be able to do in the what IDC called the second platform, second IT platform, today it opens up to for the rest. So that's the whole idea. That's why the this Hadoop coin, which has primarily a MapReduce data processing capability phase and a Hadoop file system phase. A quick example. What is it? So how things happen in a MapReduce function? So a simple example, an oversimplification. What if I have this sentence and I want to just pass a job across, call a MapReduce function, and I want to find out on my Hadoop file system how many times each one of these words have been repeated. So what it does is it takes the request, the job, breaks it down, spreads it to the cluster nodes. Each cluster node calculates it, And that's where we have the map function coming in. And then once each node has calculated how many times it has the word repeated, it passes it to another reduce. Sorry? I have maybe 2 more slides on that. Okay. So, and then that's where, and then it gets reduced to the results. So that's how the map reduce function propagates into the cluster, making use of every server in the cluster. If you remember, we only said map reduce and Hadoop file system. Well, once Hadoop has been adopted by the Apache Open Software Foundation, they have put a lot of small little tools, beautiful ones, things like I can have an SQL query, querying, SQL-like querying language on top of my Hadoop file system. They put a small column-based no SQL database on top of it as well, adding that richness into the complete ecosystem. Done. EMC, from an academic perspective, there is a lot of EMC education programs that can be offered with the to the university, starting not only with the technology but also the methodology of the analytical cycle that needs to be taken as well. And then we have already done this. We have alliances from an academic perspective. I do apologize about this. The last ones. Gentlemen, thank you very much. I'm sorry if it was too fast. Any questions?
Quick question. Do Hadoop nodes are inverted trees? Inverted trees, you know,
when you say Hadoop, Hadoop has that file system, so that I create my data fabric on it, and I just I have my data lake. Today, from a EMC perspective, we call this data. So I put my data, and then if I'm going to do a reverse tree search, that's going to be on the higher level of the services, depending on if I go to that last, very quickly, to this diagram. Oops, this one. The rest of the layers that you put on top of it, that will provide you all the functionality. And then probably when I look at the solution from our colleague from HP, that will be probably coming somewhere, and you can correct me if I'm wrong, on a virtualization layer and some of the analytics that's going to come on top of this. I'm not sure. You'd probably be leveraging any type of a underlying data fabric as well. The answer is, one way or another, there will be a way that that will be done today. And the emphasis in a university is, these are all out of research, open source research results. Ideal to go in each one of them, it's a project to improve, evolve, etc. And then you need, for example, some of them are column-based database. Some of them are more database suitable for maps. You need to have that specialization, especially if you look at the math and the enormity of the data that you are challenged to look at to get insights from.
Thank you very much.